Hello, Physics 1, Mr. G. So I'm going to show you how to work some more problems with Newton's laws. All right? So here we go. Here's a table, all right, of some kind or another. And here's the floor. And what do we have? A pulley. Okay? And then there's a block. Of course, there's always got to be a block. Sitting on the table. And there's a string attached to the block that goes over the pulley and is, guess what? It's attached to another block. Yeah. So let's give these blocks names. Joe. Actually, yeah. Why not? Here's Joe. Okay, and then this block is Sally. All right. So Joe has a mass of 1 kilogram. And Sally has a mass of 0.5 kilograms. Okay? And so for right now, let's say there is no friction. No friction. Between the surface of this table and Joe. Okay? And we could get in the lab, we can actually get fairly close to no friction. What we do is we replace Joe with one of those dynamic carts that we use. Right? The ones from Pasco. Because those have wheels with bearings, and that reduces the effective friction a lot. In fact, we're going to be doing labs like this hopefully next week. Hopefully. Yeah, I do plan on coming back to school. All right. So the question is, if I release the system from rest, what's it going to do? All right, so release from rest. Specifically, let's figure out what is the acceleration of Sally going to be. All right. And then also, possibly, maybe, what's the tension in the string? Okay. So, yeah, you're going to work this problem out by using Newton's second law. And because there are two objects here, I am initially going to draw two three-body diagrams. You really, really, really should pay attention to this, because after this little presentation, I'm going to ask everyone in class to do some problems like this, take a picture of them, and then send me those pictures via Teams, as in by the end of class. So there you go. Okay, pay attention. And you can always watch this video again, all right? I'm going to try not to ramble very much here. Anyway, so here's what we do. Let's draw a picture of the first mass, Joe. I'll put a little... All right, so here's Joe. Right, it's sitting on this table, and Joe's mass is 1 kilogram. And there's a reason I'm not going to keep Joe, because I'm going to end up writing down this mass, okay? And it's easier if I just say that Joe, let's call Joe, I know it's boring, but M1, okay? So M1. So the forces acting, that's what a free body diagram does. You draw all the forces acting on the object, all right? So hopefully you realize one of those forces is the weight of Joe. The weight of M1, that acts straight down, and that's equal to M1G. It's important that you label these masses because they're not the same. You've got two of them in this problem, so you need to keep track of which one is which. There's also the force that the table exerts up on this mass. That's called a normal force. n. And finally, there's the string attached to it that exerts a tension force. There's no friction to worry about. So that's it. That's the free body diagram. All right. Next, I'm going to write Newton's second law, which states that net force equals ma. So with this picture, so in the vertical direction, I'll indicate that by putting a subscript y here. And the same with the acceleration. Well, it's not accelerating up or down. So the net force in the vertical direction is 0. And of course, that just means that n is equal to m1g. But that really doesn't help us find acceleration. Okay, what about the horizontal direction? Now, you won't always have to keep track of vertical and horizontal separately. I'm just doing it now to show you, indeed, the vertical forces cancel each other out. Also, I'm going to choose a direction here for acceleration, a coordinate system. So I'm going to call this direction positive. So with that in mind, the net force in the horizontal direction is just T. And so according to Newton's second law, that's equal to m1a. And I'm just going to leave this as a here, okay? And that's it. I can't do anything else. There are two unknowns in this equation. T is an unknown, and a is also an unknown. So draw a free body diagram of the other mass. Okay, so the other mass is the one suspended from the string. So that free body diagram is going to look like this. There's an upward force being exerted. That's the force in the string. It's T. Yeah, it's the same T that's over here. Okay, the same. And then the downward force, this is M2 also, keep in mind, Sally. The downward force is, there's a force of gravity acting on Sally, downward. And that force is M2 times G. Okay. Now, I'm going to write Newton's second law for this thing. So the net force on this is equal to its mass times acceleration. For this problem, I'm letting the positive direction be whichever way each of these guys is accelerating. So for this M2, I'm going to call down positive, because I know it's accelerating downward. Yes, it will be, but it's not in free fall. Okay? So with down being positive, net force is expressed as M2G minus T equals M2A. It's Newton's second law. All right, the net force, there are two forces here, and the net force is their difference in this case. Yeah, they point in opposite directions, so I get the net force by subtracting them. And so once again, I have an equation that has the same two unknowns. I have T, right, that I don't know, and I have the acceleration that I don't know, but I know that these are the same in each of these free body diagrams. So I could do the whole algebra thing here, substitution. I know that T is equal to M1A. So I could replace T with M1A. And that's equal to M2A. Yes, this is getting a bit more abstract as we proceed through the year. Okay? Oh, yikes, we're really in the realm of algebra now. If I want to solve for A, I need to get all the terms with an A on one side. So how about we add M1A to both sides? And then finally, I'm going to erase this stuff over here so I have more room. Remember, you can rewind this as many times as you like to view it again, which you probably should do. Okay, so M2G equals M2A plus M1A. If I want to solve this for A, I need to basically unfactor the A out of this term. You can do that. This is the same as M2 plus M1 times A. And then finally, divide both sides by M2 plus M1. And so that makes it cancel on the right. And voila, we have the answer. The acceleration of this thing, I'm going to flip around here. So that acceleration, and they both have the same acceleration, is M2G over M2 plus M1. Okay. So, and really at this point, you're really done with the problem. I know you loves to plug in the numbers, and we can certainly do that. All right. Let me erase some more of this stuff here. And then we're going to do a couple of more things with this solution just to make sure that it makes sense to us. But really, honestly, getting a numeric value for this acceleration is the least important part of the problem. Essentially, when you get this expression, you're done. Okay, so A is going to be, so M2 was 0.5. Times G, which is about 10. Divided by M2 plus M1, so 1.5 kilograms. So A is 0.5 times 10 is 5 meters per second squared. Divided by 1.5. Actually, there's a kilogram here, sorry. You got to keep this unit with you. Okay, so then the kilograms cancel out. You've got meters per second squared, and A is 5 divided by 1.5, whatever that is. All right, I have no idea. Hold on. Okay, it's 3 1/3 meters per second squared. Okay, so then, yeah, problem done. Although, hang on a second here, okay? Let's take a look at this solution here again and see if it continues to make sense under other conditions. The other thing is this, okay? Please, don't try to memorize this equation. You can, but there's going to be a ton of different methods that leave us different expressions for accelerations and velocities, etc., etc., etc. What you need to know how to do is draw a free body diagram and write Newton's second law. All right? So, for example, so here's M1, and here's M2, and there's a pulley right here. So what happens, suppose that we cut the string. All right, let's cut this string. Zip. And so then what's going to happen to M2? It's going to be in free fall. There will no longer be any tension force acting on it. So its acceleration should be G. So over here in this problem, the way we can eliminate M1 Ooh, I could just scratch it off of the solution here. Imagine that. And holla playa. That goes away, and A is equal to G. Of course it is. This is very consistent. That's one of the things I just really love about doing these silly physics problems. Okay, yep. Okay, then let's look at something else, of course, and that's going to be what if M2 is 0, all right? What if, well, yeah, I cut the string here, all right, and so this is no longer here. So what is A going to do if we get rid of M2? We let M2 be 0. Well, the block's just going to sit here. It's not going to do anything. And you can see that because in the top here, if M2 is 0, that term becomes 0. And that's 0, so it's just 0 divided by M1, which is 0. So there you go. So you should attempt to work the problems listed below.